Hello, everyone. I'm very excited to be here to present Ringleader, which efficiently offload intra-server orchestration into NICs. Nowadays, online cloud services, such as search or key value store, are commonly deployed in data center. This type of application comes with 3 requirements. First, they have tight tail latency requirements. This is because their requests are typically small, and the end-to-end application performance is bounded by the slowest request completion time. As a result, they are requiring microsecond-level tail latency. Also, online cloud service requests usually have different priorities. Request priorities are determined by their execution deadline or their criticality to application performance. Lastly, data center application provider usually pack multiple applications into the same server to improve the CPU efficiency. For example, a latency-sensitive application might coexist with other throughput-oriented applications, and it becomes important to manage interference between applications to guarantee performance. To meet the above 3 requirements, existing research uses intra-server orchestration to manage service within a machine, which entails 3 aspects: load balancing, request scheduling, and CPU allocation. In load balancing, it determines which worker core to process this incoming network request. It reduces tail latency by avoiding the queuing time due to load imbalance. Request scheduler identifies different request types and determining what order this request should be processed by the worker core. For example, the memcached application might comprise 2 distinct services, which each service handles a specific type of request. The request scheduler would prioritize service A's request as it has much tighter deadline than service B. Request scheduler guarantees tail latency for critical workloads. The CPU allocator determines which application service run on which CPU cores. To mitigate interference, cloud provider isolates application across cores, and when the workload changes, the CPU allocator migrates cores between applications to ensure high resource utilizations. State-of-the-art intra-server orchestration uses centralized CPU core to make the scheduling, load balancing, and CPU allocation decisions. These orchestration tasks usually run on user space over dedicated CPU cores to guarantee microsecond-level tail latency. The advantage of such approach is that the centralized orchestrator core provides optimal performance because the core has the comprehensive knowledge of the system, and it can guarantee consistent and precise policy enforcement. However, there are some limitations of the centralized CPU orchestration. First, any core is used as an orchestrator core is hard to perform application-specific processing. This is problematic because in today's data center, CPU is a scarce resource. Secondly, centralized CPU orchestration cannot scale. A single CPU throughput limits the orchestration's task scalability. Previous research shows like even taking up a whole dedicated CPU core to run the scheduler function, you can only achieve 5 million requests per second. However, today we have hundreds of network with hundreds of worker cores inside of a server. So a problem then arises. Is it possible to achieve scalable, centralized intra-server orchestration with minimal CPU overhead? And the answer is yes. We can achieve it by using smart NICs. Modern NICs offer 3 unique opportunities for this problem. First, NICs sit at the centralized point of the network, as all network requests must pass through the NIC. Second, NIC accelerator can be designed to operate at full network line rate to meet the scalability requirements. Lastly, offloading orchestration tasks into the NIC hardware could free up the whole CPU core and to remove the inter-thread communication overhead. We present Ringleader, which is a new NIC architecture that utilizes novel hardware offload to perform orchestration. In Ringleader, scheduling and load balancing are performed by hardware offload inside of the NIC. Core allocation is performed cooperatively between the NIC and host. Then the NIC will have a load monitor to monitor each application's queuing condition and generate reallocation hint to the host. The host will use the data path OS to perform OS management functions that includes core allocation, buffer management, network transport, as well as task multiplexing. We have chosen to use the data bus OS instead of traditional OS because traditional OS abstraction imposes high overhead in multiplexing and context switching. Lastly, Ringleader provides a new data path OS to NIC interface that allows the NIC to communicate orchestrated metadata with the host at very fine granularity with little PCIe and CPU overhead. And in today's talk, I will focus on the load balancing and scheduling design. Check our paper for our interface and our CPU allocation. There are 3 design questions we want to answer. First is how to divide the labor between the host and NIC, and as simply offload everything to the NIC will lead to less effective orchestration. Once we split the function between the host and NIC, the next question is how to coordinate between these components, because otherwise it will lead to pathological priority inversion problem. The last question is how to design the NIC hardware to achieve efficient and high-performance orchestration. The architecture must be crafted carefully to operate under tight hardware constraints. The first question is to how to divide the labor between the host and NIC. A naive way to offload is to offload all aspects into the NIC hardware. That means the NIC will have a centralized request buffer to buffer incoming requests, and a hardware scheduler to reorder requests based on their priority, and then a hardware load balancer will steer the highest priority request to the idles when a CPU core becomes idle. This could achieve the centralized single queue scheduling and load balancing policy. However, in reality, there is a PCIe communication delay between the host and the NIC. So if the load balancer only steers packet to the core when the core becomes idle, it will lead to poor throughput and stop and wait problem. Therefore, each worker core has to have a per core buffer to hide the communication latency. But this could lead to head offline blocking. Here is an example. We have 2 services running on core 1 to core 4, and the service A has higher priority. A burst of service B's packet arrived and been spread across all worker cores. And after that, a service A's packet arrived, and it has been blocked after service B's packet inside of the per core buffer, lead to head offline blocking. So therefore, in Ringleader, we unload part of the scheduling function into the host. That is, each worker core would have a very shallow priority queue, and each core uses this priority queue to locally schedule requests preemptively to avoid head offline blocking. We keep this queue shallow as we want to keep as much of the scheduling function into the NIC hardware. The second question is how should the on-NIC load balancer coordinate with this software scheduler? A naive way to do load balancing is just to use join bounded shortest queue, which steers requests to the core which has a minimal queue length, and the host queue has a maximum depth of n packets. However, we found out Gbps queue does not make the suboptimal load balancing because it ignores the software's scheduler's behavior. Here is an example. Let's say we still have 2 services running on core 1 and core 2, and when A's request arrives, which is the highest priority request, Gbps queue will steer it to core 2 because it has a minimal queue length. However, this is not the optimal decision because if the package is steered to core 1, it will be served before the green packets, so core 1's ideal queuing time will be smaller than core 2. To overcome this limitation, we come up with JBSRQ. In JBSRQ, the NIC will steer packet to the core, which has a minimal rank, and each core has a maximum rank of n. The rank is calculated as follows. Let's say we are calculating service A's rank, service A's packet rank on core C. Qx.core C represents service X packet count on core C. And the first term just add up the sum of request count for those services that has higher or equal priority than A. The insight here is rank should contribute by those higher or same priority requests because they were served before A. The second part of the formula calculates the sum of request count for service that has lower priority than A and multiplied it by a constant factor lambda. Lambda is between 0 and 1. The insight here is lower priorities request queue count matters less, but we should not completely ignore them. This is because if a low priority request is currently taking up the CPU, there is a cost of preempting it or waiting it to yield before scheduling an incoming high priority request. So here is some running example show how JBSRQ work. So use our previous example, JBSRQ will steer the read packets to core 1 because the calculated rank is small and because it just mostly ignores base queue length. For another scenario, we are steering packet, service B's packet, and it will take into account of both A and B's queue length, so the packet will be steered to core 2, which is the optimal decision here. In conclusion, JBSRQ coordinate with the host priority queue and achieve optimal for both high and low priority requests. The last question is how to design the architecture of the load balancer and scheduler. In Ringleader, the hardware scheduler is implemented as a hardware priority queue. It reorder service based on their priorities and always dequeue the frontmost highest priority service request. The hardware load balancer tracks the service to core mapping through a bit mask. And for an incoming request, it will first look up the bit mask and use the rank calculator to calculate rank for those cores that run this service. And the calculated rank is then sent to a reduced tree to find the minimal ranked core. According to JBSRQ, only if the minimal ranked core's rank is smaller than the bound, it can be dispatched. Then you might be aware of a problem, that the scheduler might schedule a request that cannot be dispatched by the JBSRQ. The right figure shows an example. The hardware scheduler will schedule the frontmost read packets. However, all the cores that run in the service A reach the rank bound. So the read packet cannot be dispatched from the load balancer and block the whole hardware pipeline. And the green packet inside of the hardware scheduler cannot be scheduled, even if core 4 and core 3 are staying idle and could process that packet. To solve this problem, we come up with non-blocking interface between the hardware scheduler and the load balancer. The load balancer will provide a bit mask to tell the scheduler like which service is eligible to be scheduled. We define a service is eligible to be scheduled only when those cores running this service has at least one core with a rank smaller than the bound. So inside the hardware priority queue, it will evaluate each element's eligibility and dequeue the frontmost eligible elements. We properly designed the hardware architecture to efficiently maintain this eligibility mask, as well as making sure our load balancer and scheduler can fully pipeline. So Ringleader can schedule and dispatch packet at every single cycle. For implementation, we implement our prototype using FPGA, using 4K lines of Verilog code. And we build a user-space NIC driver for our Ringleader NIC that provides a DPDK-like kernel bypass access to our NIC. Also, we integrate Ringleader with the data pass OS with demi-kernel using 800 lines of Rust. For evaluation, we test Ringleader over synthetic benchmark as well as ROC's DB application. And we compare to 3 baselines, including Shinjuku, Caladan, and RSS. In today's talk, I will focus on the synthetic benchmark result and Shinjuku comparison. So the first question in our experiment we want to answer is how Ringleader's design decision contributes to its overall performance. We compare Ringleader with its reduced version, that the reduced version just removes a single component from default Ringleader. The figure shows how high priority request tail latency changed with the overload. Let's first see what happens if we remove the software priority queue. As we can see from the figure, like without software priority queue, the saturation point is much earlier than the default Ringleader because the host significantly increased the latency because of head-of-line blocking. Next, we disable JBSRQ and use JBSQ instead. As we can see from the result, high priority request, the tail latency is much worse than default Ringleader. Then we disable the eligibility mask between hardware component, and also the latency is much worse than default Ringleader because the hardware suffers from blocking issues. In conclusion, software priority queues, JBSRQ, and eligibility mask ensures that Ringleader can achieve effective orchestration. The next question we want to answer is how does Ringleader compare to the state-of-the-art CPU-based orchestration? And we compare to Shinjuku. We can see from the result, like Shinjuku, because it's bounded by the single core's performance, its throughput is limited around 3 or 4 million requests per second. However, Ringleader can scale much more than that and achieves better scalability than the software-based approach. In conclusion, Ringleader achieves better performance and scalability than the software-based approach. In conclusion, Ringleader offload orchestration through a new load balancing and scheduler, load balancing algorithm and scheduler, as well as a new OS to NIC interface. We do experiment on 100G FPGA NICs and show Ringleader offers good tail latency and high throughput. Please check out our code under this link. Thank you. And I'm happy to take any questions.